Hey YouTube listeners, this is Abigail Visitacion and I'm here again to give some examples of higher order differential equations and how to solve them. So let us proceed to example number 1. Y triple prime minus 2y double prime minus 3y prime plus 10y is equal to 40 cosine x, which is a non-homogeneous equation. So to solve a non-homogeneous linear differential equation, we must do two things. First is to find the complementary function, and second is find any particular solution of the non-homogeneous equation. We all know the general solution, which is y is equal to yc plus yp. The complementary function yc is the general solution of the associated homogeneous dE, that is y triple prime minus 2y double prime minus 3y prime plus 10y is equal to 0. So factoring this, and we'll get m1 is equal to negative 2, which is a real root, while m2 is equal to 2 minus I, and m3 is equal to 2 plus I, which is complex roots. I assume you already know how to get its corresponding solutions, so we'll proceed to the complete complementary solution obtained, which is yc is equal to c1 e to the negative 2x plus e to the 2x times quantity c2 cosine x plus c3 sine x. So let's proceed in finding the particular solution. The g of x in the given equation is cosine function, so in this case we can use the method of undetermined coefficients. The underlying idea behind this method is a conjecture about the form of yp, an educated guess, that is, motivated by the kinds of functions that make up the input function g of x. Now, since the function g of x is again a cosine function, a natural first guess for a particular solution would be a cosine x. But because successive differentiations of cosine x produce sine x and cosine x, we are prompted instead to assume a particular solution that includes both of these terms, which is yp is equal to a cosine x plus b sine x. Differentiating yp and substituting the results into the differential equation gives a sine x minus b cosine x minus 2 times the quantity negative a cosine x minus b sine x minus 3 times the quantity negative a sine x plus b cosine x plus 10 times the quantity a cosine x plus b sine x is equal to 40 cosine x. After regrouping, we will then have 4a sine x minus 4b cosine x plus 12a cosine x plus 12b sine x is equal to 40 cosine x. In here, we can get systems of equations, which is 4a plus 12b is equal to 0 and 12a minus 4b is equal to 40. Using elimination, we can obtain the values of a and b, which is 3 and negative 1 respectively. Substituting these values to your particular solution, you'll get 3 cosine x minus sine x. Now that you have both your yc and yp, your general solution would be y is equal to c1 e to the negative 2x plus e to the 2x times the quantity c2 cosine x plus c3 sine x plus 3 cosine x minus sine x. Let's proceed to example number 2. Y double prime plus y is equal to x to the 1/2. Again, it's a non-homogeneous equation. For finding its complementary solution, we must get its auxiliary solution. In here, its roots are complex, which is m is equal to positive and negative I. Just like in the previous example, we then have its complementary solution. yc is equal to c1 cosine x plus c2 sine x. We now compute the Wronskian of yb1 of x and yb2 of x, which is equal to cosine squared x plus sine squared x, which is equal to 1. Let f of x is equal to square root of x. Let v1 of x is equal to the negative integral of f of x yb2 of x over w of x dx, and let v2 of x is equal to the negative integral of f of x yb1 of x all over w of x dx. Using variation of parameters, the particular solution will be given by yp is equal to v1 of x yb1 of x plus v2 of x yb2 of x. We now compute v1 of x and v2 of x. v1 of x is equal to the negative integral of square root of x times sine x dx. Evaluating this, and you'll get square root of x times cosine of x minus square root of pi over 2 times c times the quantity of square root of 2 over pi times square root of x. v2 of x is equal to the integral of square root of x times cosine of x dx. Evaluating this, and you'll get a negative quantity of square root of pi over 2 times s times the quantity of square root of 2 over pi times square root of x plus square root of x sine x. Thus, we obtain our yp, which is equal to cosine x times the quantity square root of x cosine x minus square root of pi over 2 times c times the quantity of square root of 2 over pi times square root of x plus sine x times the quantity of negative square root of pi over 2 times s times the quantity of square root of 2 over pi times square root of x plus square root of x sine x. Simplifying further your yp, you'll then get the general solution, which is y is equal to yc plus yp is equal to c1 cosine x plus c2 sine x plus 1/2 cosine x times the quantity of 2 square root of x cosine x minus square root of 2 pi times c times square root of 2 over pi times square root of x plus 1/2 sine x times the quantity of negatives square root of 2 pi times s times square root of 2 over pi times square root of x plus 2 square root of x sine x. Let's proceed to the last example. Find the deflection of a thin vertical homogeneous column of length L subjected to a constant axial load P if the column is hinged at both ends. The boundary value problem to be solved is EI y double prime plus PY is equal to 0, where y of 0 is equal to 0 and y of L is equal to 0. First, note that y is equal to 0 is a perfectly good solution of this problem. This solution has a simple intuitive interpretation. If the load P is not great enough, there is no deflection. The question then is this: for what values of P will the column bend? In mathematical terms, for what values of P does the given boundary value problem possess non-trivial solution? By writing phi is equal to P over EI, we see that y double prime plus phi y is equal to 0, where y of 0 is equal to 0 and y of L is equal to 0. If we recall, for phi greater than 0, we write phi is equal to alpha squared, where alpha is a positive number. Therefore, the auxiliary equation that we can obtain is m squared equals positive negative alpha I. Thus, having a general solution, y is equal to c1 cosine alpha x plus c2 sine alpha x. Having the condition y of 0 is equal to 0, it will yield c1 is equal to 0, and so y is equal to positive c2 sine alpha x. Now the last condition is y of L is equal to 0, or c2 sine alpha L is equal to 0, is satisfied by choosing c2 is equal to 0. But this means y is equal to 0. If we require C2 is not equal to 0, then sin alpha L is equal to 0 is satisfied whenever alpha L is an integer multiple of pi. So, alpha L is equal to n pi, or alpha is equal to n pi over L, or phi n is equal to alpha squared n is equal to the quantity n pi over L raised to the power of 2, where n is an integer. Therefore, for any real non-zero C2, y equals C2 sine n pi x over L is a solution of the problem for each n. Because the differential equation is homogeneous, any constant multiple of a solution is also a solution, so we may, if desired, simply take C2 is equal to 1. Going back to the given equation, we see that the deflections are y equals C2 sine n pi x over L corresponding to phi, which is phi n is equal to Pn over Ei is equal to the quantity n pi over L raised to the power of 2, where n is an integer. Physically, this means that the column will buckle or deflect only when the compressive force is one of the values. Pn is equal to the quantity n pi Ei over L raised to the power of 2, where n is an integer. These different forces are called critical load. The deflection corresponding to the smallest critical load, P1 equals quantity pi Ei over L raised to the power of 2, called the Euler load, is y1 of x equals C2 sine quantity pi x over L and is known as the first buckling mode. I hope you have enjoyed and learned something from my video. See you next time. Thank you and God bless.